welcome to space. Now, getting into orbit has always been a question of sitting on top of a rocket and aiming upwards. But what about getting back down again? In fact, re-entry is one of the biggest challenges in the modern space business. We're going to find out how it's done, but first some more news from the universe this month. The Orion spacecraft is preparing for its first unmanned test flight on the 4th of December. It's the first probe for decades to be designed to send humans deep into space. This is the first ever photographic proof of water ice on Mercury. The images from the Messenger spacecraft show an icy deposit in a crater near the planet's North Pole. And the Cassini-Huygens mission has released this stunning visible light photo of Saturn's moon Tethys amongst the planet's trademark rings. To our main story now, and Europe has just built a new spacecraft, the IXV, and it's about to face the challenge of re-entry. This rarely seen footage shows one of the most stressful moments in spaceflight. This is re-entry, the make-or-break moment when satellites burn up and astronauts hang on for the ride of their lives. 53 seconds. You can't recreate it in the lab. In fact, to really learn about re-entry, you have to go to space and fly back down again. ESA's newest spacecraft will do just that.
This is the IXV spacecraft, is the model that is going to be launched, is the flight unit that's going to be launched on Vega in November this year.
While a past IXV prototype sits on display, the real space-ready version is facing the ultimate re-entry challenge. Giorgio Tumino runs the project.
The objective of the mission of the IXV is to master all those grey areas that we don't know about atmospheric re-entry.
To fill in those gaps in our knowledge, the IXV will lift off on a Vega rocket to an altitude of 430 kilometers, as high as the International Space Station, and then fly back to a targeted spot on Earth. Right now, it's being prepared for its flight in November.
Starting from the front, we have the avionic bay. You can see the operators are currently testing a part of it. This is the rear part of the vehicle. We have the four reaction control thrusters. What you see black is ceramic thermal protection, so a very highly performing material. And what you see here, you see some dots where there are the integrated sensors. So we have a pressure sensors, strain gauges integrated into the vehicle.
Getting back to Earth from space is not a walk in the park. During re-entry, speed turns to heat. The IXV will reach 28,000 kilometers an hour in space, and as it comes down, the friction of Earth's atmosphere will heat the nose cone and steering flaps to 1800 degrees Celsius. That heating reaches its peak at a very specific altitude in our atmosphere, a zone where you either make it or you don't, according to re-entry guru Jose Longo.
For vehicles that are not designed to have a re-entry, like the normal spacecraft, satellites, all them break between 80 to 75 kilometers.
To find out more, we met up with ESA's master of space junk, Holger Krag. He monitors debris that's in orbit and falling to Earth. To show us the kinds of forces the IXV will face, he talks us through video of the ATV resupply ship breaking up as planned during re-entry.
This corresponds to roughly 100 kilometers altitude. The ATV is already glowing hot. You see quite some tiny fragments falling behind. This is mostly the solar arrays that are sticking out. They fall off first. They're just sheared off by the aerodynamic forces. This is at roughly 75 kilometers. You saw this flash and the cloud of gases leaving behind. That was the explosion, interaction of the fuel with the atmosphere, self-ignition. Now we are at 60 kilometers. You see very high temperatures, really white glowing objects. There are objects falling behind. That's because they are very lightweight.
This whole re-entry process happens in a very short amount of time.
From the point where you have done the re-entry maneuver to ground, that's roughly half an hour. From the point where your spacecraft starts to get hot, that happens at around 90, 80 kilometers, to ground, that's just 10 minutes.
So the IXV will fly through our atmosphere in a matter of minutes. One of the key elements that ESA engineers are testing is its innovative shape. For the moment, re-entry capsules for astronauts are flat-bottomed like the Soyuz and new Orion spacecraft. They're reliable, but not easy to land in targeted areas. NASA's winged space shuttle could land on an airstrip, but it was complex, and in 2003, damage to its heat-resistant tiles led to the tragic Columbia disaster. The IXV is different. It's what's known as a lifting body shape, halfway between the two, offering controllability and maneuverability.
So here are the ceramic flaps. They will withstand the temperature which are in the order of 2000 degree Kelvin. They will move to control the vehicle around the flight, so to steer the vehicle, to change the inclination of the angle of attack.
The IXV flight will bring fresh data about the real conditions of re-entry that we need for space exploration.
When we look at the future possibility to bring back to Earth astronauts or samples from asteroids, or in the long term from Mars, this is a technology that is a must to have on board to be able to come back to Earth.
Neither simulation in computer nor simulation in facilities like a wind tunnel represent the reality. Therefore, at the end, you need, in any case, to fly.
As we dream of travelling far beyond our planet, we should always keep in mind that we need a safe way home. We're at the European Space Operations Centre in Germany, and behind me in that building, the team are controlling the Rosetta spacecraft. Let's see how they're getting on. These are tense times for the Comet hunters as they run through simulations of the landing sequence when Philae leaves the mothership Rosetta and flies down to the comet.
Now we are in the close observation phase, and slowly and gradually we have started orbiting the comet at lower altitudes. Of course, it can happen that at any time the comet becomes very active and pushes the spacecraft completely away from its trajectory. But this we cannot predict. The softer the surface is, the more likely is for the lander to have a soft landing and have higher chances not to flip over. Ciao Rosetta. In a few weeks, the top time of your life is coming up. When the baby goes, don't shake too much. Be reassured that it will gently touch down here on the comet. Let it go. It's the time now to let it go. Ciao, all the best.
Well, that's it for now, but as you heard, next month Rosetta reaches the pinnacle of its mission. We'll be here with the team to share the moment. See you then.